Okay, we started today with a question. If I fill this container with water up to this point, and then after that, I add water from here up to here. It's about 20 centimeters, okay? Then what's holding up this water? And everybody pretty much said, yeah, the water below it. Good. Then I said, okay, let's assume that the area of this circular chunk of water down here, this circular surface that's holding up all the water above it is 15 square centimeters. I said, okay, so how much weight is it holding up? Well, people pretty much got pretty far on that. Some people, I think, completely got it. But what we have is now this is actually circular, so let's try to make it look circular. So we've got like this circular disc of water down here. It's holding up water up to this level. And we know that this is the water level because you see waves and shark fins and stuff. Okay. I'm just kind of making it wavy and shark fin. So you got 20 centimeters of water here. You got a 15 square centimeter cross-sectional area. And the surface here might be a little hard to read that, but the surface here holds up the 20 centimeter column. That's where the force comes from to keep that column from accelerating downward at 9.8 meters per second squared. Okay, so question is, how much force? The answer is, well, force is the weight of the 20 centimeter column. Fifteen square centimeters times 20 centimeters, 300 centimeters cubed. At 1 gram per cubic centimeter, which everybody's had chemistry or any kind of a physical science course should have deeply ingrained. And if not, it's not your fault because you're smart. It's the way it's been taught. Okay. And not throwing stones at anybody because every teacher has to deal with what they got to deal with. Okay. So I'm not in their shoes. I'm not going to throw stones. I think our whole educational thing is screwed up, but you probably don't want me to be the one to fix it. Okay. Now, at 1 gram per cubic centimeter, mass is 300 grams. The weight is 300 grams times 9.8 meters per second squared. And that's not 3,000. Okay. Because you got to do the units. And grams times meters per second squared doesn't give you newtons, does it? And I'm not gonna get my hands dirty explaining that because everybody here did well first semester. If you don't know how to translate that to 3 newtons, you're gonna have to think through it and lock it in, because you'll keep stumbling over it if you don't. Okay? 0.3 newtons. Okay. Then I asked, how much force per square centimeter is that lower surface? And that's going to be, well, three newtons over 15 centimeters squared is 0.2 newtons per centimeter squared. What's this? In the SI unit, newtons per meter squared. That is pascals. Well, 1 meter squared is 100 centimeters squared, which is 10,000 centimeters squared.
Why it's squared? It's because it captures a picture.
And then you can say 0.2 newtons per centimeter squared
Plug in 0, 0 squared.
multiplied by 10,000 centimeters squared per meter squared.
Plug in 1 squared into 1, so we can get 1. If you plug in 2, what do you get with 2 squared? 4. Squared is 4.
Comes out about 2,000 pascals. Okay.
Plug in negative.
Now, what's atmospheric pressure? You might know it's 760 grams of, or millimeters of mercury. That's a column. Mercury's about that high, 700, about 760 millimeters is about 3/4 of a meter. Okay. Mercury is very dense. How much water would it take? Well, mercury is, I think, 13.6 times the density of water. So you multiply it 760 millimeters by 13.6, then you get about 30 feet, or about 10 meters. Those are ballpark, but they're pretty close. Would it make sense that a 10-meter column of water would have a pressure of 760 millimeters of mercury, or about 10 meters of water? I think I just said something circular there. Well, atmospheric pressure is approximately 100,000 pascals Now, that's not quite 760 millimeters of mercury. Okay, it's about 2% low. Take off 2% of 760, you get, I think, 746, 745, 744.8, something like that, millimeters of mercury. And that's about what it is here, because we're 2,000 feet altitude. Okay, sea level, it's a little higher, because you get a little more air. Now, air acts just like water. Okay, the air above my hand is being supported by the air that was right here before I put my hand here. Just the air directly above my hand, not the air out there or out there, the air directly above my hand. The air directly above one of these tables is being supported, well, by the surface of the table, I guess. But if you take the table away, it's being supported by the air that's where the table was. Just like the water is being supported by the cylinder water, or the circular disc of water below it. Okay, that's how pressure works. Pressure also squeezes out. You know, squeeze a balloon with some holes in it. Water's going to spurt out in the direction perpendicular to the surface, which tells you something about the direction in which pressure acts, perpendicular to any surface. Okay, you don't have to read about it, but that's a synopsis of pressure. One kind of neat thing, if you've got any objects in a container underwater, you can tell there's a water surface, there's a shark's fin. Okay. You hear about a bunch of people getting bitten by sharks in Australia? There's something with a lot of rain and the density. I didn't catch it all. And a lot of sharks moving around. And I don't think anybody got critically injured because they probably didn't get bitten by the big sharks. But, you know, still, you don't want to get bitten by any shark. Much worse than getting bitten by a dog. Okay? You get salt in your wound right away. Unless it's a freshwater shark, that's the one you want to get bitten by. Well, okay, there's a cube. Okay. Water pressure is acting on the cube from below, from the sides, and from above. Now, I just drew one arrow below and one arrow above, but let's say there's an arrow for every for every square centimeter of the surface, okay? Which arrows are going to be longest? The ones up here, the ones down here, the ones over here, the ones back here. Which arrows are going to be longest? Just use your thumb to point in the direction of where the arrows are going to be longest. Where's the pressure greatest? Pressure is greatest when the depth is greater because you got to support more water. Now you're not actually supporting water at this point, but the water over here is supporting the water above it, and the water over here is supporting water above it. And that's squeezing the water underneath here, so it pushes up. Now, it's just a vague conceptual thing, but it comes out that since the pressure down here is lower than the pressure up here, you got buoyancy. You can extend this to any three-dimensional object. All you need to do is use a little multivariable calculus. The integral theorems in multivariable calculus. Everybody remembers those, right? The two of you have had this course. You might just ask your AI, how is it that multivariable calculus proves Archimedes' principle? Okay, that's a neat connection. I think AI would give you a good explanation, and if it does, copy it and send it to me. I'd like to see what they say. I'm asking AI way too many things. I'm asking AI to translate all my classes into something that's ADA compliant, and it's doing really well, but it still has some rough edges. It does great stuff, and then there'll be just some bonehead thing in there. And I don't call it a bonehead because I don't want it to get mad at me. But I just say, hey, this implies that this thing ought to be a straight diagonal when clearly it's a curve. It doesn't know. It is moving in kind of diagonal direction, but there's a curve. But, you know, it has no concept of what it's saying. But it puts the words together beautifully. Not beautifully. There's no poetry, there's no beauty to the words, but it's very clear, which can be beautiful in itself. Just ongoing commentary on AI when it comes up into my head. Think about it. And I'm going to run this transcript through AI and I'll be interested to see if it picks up on it. Says, hey, who you calling an idiot? If it comes out with that, I know that AI is almost humanly intelligent. And if it doesn't, I think it's still a ways to go. All right. Well, and of course, we've got arrows over here. You notice that the lower arrows got longer, right? The lower the arrow, the longer it was. So there's a net force upwards. The force is here, don't push upward. Only the force down here pushes upward. If it's an irregular object, that's where you need multivariable calculus, and I'm not going to go there. You got to talk about normals to the surface and all kinds of stuff, and use Stokes' theorem or divergence theorem, all that stuff. Okay? So look what you got to look forward to. It really is neat to know these things. And depending on your field of engineering, it will be important that you know those things at that level. So I do recommend that as something you at least think about. And if you have trouble thinking about it, ask AI about it, just to refresh yourself and keep your mind in the context of the stuff you're going to be reading and working with in the last 2 years of your engineering education. Okay. Now, this is a pretty simple exercise here, but you guys made some mistakes. Okay, 100 square centimeters in a square meter? No, write it out. What's a square meter? It's the square of 100 centimeters. It's not 100 square centimeters. Okay? Use the units, do the dimensional calculations. And you have to understand that that's really good advice for an engineer or for anybody. But for an engineer, it's particularly important because you don't want to make those mistakes. You want to work on an interesting project, don't make those mistakes. You want a promotion, don't make those mistakes. Also, you got to learn a lot of other stuff. Okay. And of course, I'm not an engineer. I've not worked as an engineer. But of course, I went to school with a lot of engineers and had a lot of engineers come through here. I've got some sense. But if anything I say contradicts what your engineering professor says, listen to him. Okay. Well, amid many digressions, here's one simple fact. It's summarized by change in pressure is density times gravity, acceleration of gravity, times the change in your y coordinate. So as we move from here, 20 centimeters up here, delta y is 20 centimeters. Okay. I'd multiply rho by g, and I get what? Well, rho is in SI units. Okay. It's 1,000 kilograms per cubic meter, which is the same as 1 gram per cubic centimeter, because there are 1,000 cubic centimeters in a cubic meter, and 1,000 kilograms. 1,000 kilograms is 1,000. That's a kilogram. Okay. So if you apply this, you bypass the need to do all this reasoning. But the thing I keep preaching is, if this is all you don't know why. And if you don't know why, you can't visualize what in the world is going on as well as if you do know why. And you can't understand the system as well. And if you can't understand the system as well, you're not going to be as good an engineer. And you also won't have the thinking skills to, participate in what's left of society after AI gets done ravishing us, if we're not careful. So maybe even learn to be careful about AI. Well, things get a little crazy here, but that's it. And this calculation will give you exactly the same thing that this does. Rho is 1,000 kilograms per cubic meter. G is 9.8 meters per second squared. So you got approximately 10,000 newtons per meter. Yeah, newtons per. No, I'm losing track of the units. Okay. That's in kilograms per cubic meter. That's in meters per second squared. So the meters is now a -1. And delta Y is 1. I'm getting the wrong units, but work it out. You'll get the right units. You write it out. My head is not working properly. If you multiply 10,000 by 0.02, this comes out 10,000. Okay. And that's 0.02 meters, 20 centimeters. 10,000 times 0.02 is 2,000. Okay. This is what's really going on. There's a formula for it. Got a question? Okay, it's quite about weight per cubic meter or something like that. And I've even forgot what the question was, but because I got into this, but my answer was, this is in kilograms per cubic meter. Rho is in kilograms per cubic meter. G is in meters per second squared. The kilograms times the meters per second squared give you newtons. See here, the rho G is newtons per meter cubed. Okay. If you multiply that by meters, you're going to get newtons per meter squared, which is the unit of pressure. And that's it. And as I said then, for water, this is 9,800 newtons per cubic meter. I just round that to 10,000 because it's more intuitive. And you multiply that by the 0.02 meters, you get your 2,000 newtons per cubic per square meter. Okay, your pressure. All right. Okay, well, next question. Let's say there are 25, this is pretty full, there's 2,500 newtons per square centimeter, or for 2,500 newtons per square meter down here. Okay, and I'm holding it back with my thumb. Well, it's a lot of newtons per square meter to hold back. There's not much of a square meter there, so I can't even really feel the pressure. Okay. Now, if it's full and I take my finger off of here, what happens? Water spurts out. How does that happen? There are two ways to look at it. There's a change of potential energy in the system. Okay, you're losing a little bit of water up here and it's reappearing down here. And there's less energy in the system than there was. But there isn't, although there is. In the ideal case, there isn't less energy in the system because there are no dissipative forces in the ideal case. This is not an ideal case, and we know there's a little friction involved, but let's just take the ideal case. And whatever your change of potential energy from the water here to where it is down here, whatever that change in potential energy is, that's your change in the kinetic energy of the water, and the water comes out with the according speed. That's pretty simple. Now there is dissipation. Okay, you lose about maybe 30% of the whole of that size in that length, and I'm just ballparking that. I could be off by 1,000% or something like that. Don't take that literally. My intuition's around 30%, but I've not quantified that recently. And,
I will, for the moment,
we're gonna measure it in lab anyway. Friday, we will measure it. We will see what the kinetic energy of this water coming out of there is. Well, okay, let's talk about that. How are we gonna do that in lab? How are we gonna figure out how much kinetic energy is coming out? How much water, how much kinetic energy the water is carrying out at any given instant? Okay, we just had a little discussion, trying to clear up some misconceptions and so forth, or build some good conceptions. So let's just take the picture here. And we've got a tube here. I think the diameter of the tube is the inner diameter is 1/8 of an inch. I've got a drill. I can drill bigger holes, but I don't want to have to patch them. Pretty easy to patch with hot glue, but we're not going to mess with that. Because really, I want the tube because another thing we're going to investigate is how much pressure you lose in the tube is a function of the length of the tube and the speed of the water. Okay, pressure loss.
general.
Are those among you who are looking at civil engineering? Okay. Pressure loss is a big deal. And very commonly encountered, depending on just what kind of an engineering position you have. Okay, so if the water's up here, then you got a pressure down here. So what's happening in this area? Okay, well, let's just look at this. Yeah, let's enlarge it a little bit. Okay. Outside, pressure is the pressure of the atmosphere. Okay. So outside the tube, you got the atmosphere. Inside the tube, pressure is pressure of the atmosphere plus rho g y, where y is this distance. Okay, let's consider the chunk of water inside this tube. And let's say the tube length let's say it's a real short tube, so I'll just call it delta L. If it's a longer tube, we'll call it L. But to emphasize the fact that we're considering a very short tube, we're going to call it delta L. Okay, so tube diameter. I'll say radius. You don't have to mess with diameter. Tube radius is R.
So this function by the horizontal line does the task. The other hand.
I call this a water plug in the tube. It's a bad plug because it ain't going to plug the tube. It's going to get pushed out. Okay. So my question is, what's the mass of the water plug in the tube? What's the force? On the water plug? And What's its exit velocity? I'll break it down through what? Distance is the force act. What's the change in kinetic energy? What's the exit velocity? What's the exit speed of that plug? The sequence of questions, if you answer, you're halfway to Bernoulli's equation.
Find this very helpful.
Okay, so again, after discussion, we got this situation. We got a tube in the side of the cylinder, and you can kind of see where the tube comes out. If you look into the cylinder, right, you kind of see the tube in there. And the tube's actually pretty long, but we're going to consider a short tube. We say its length is delta L, its radius is R. This picture just depicts the circled area here. And I've indicated the water inside the tube. I call that the water plug. If this is some kind of a plug, pressure would pop it out. Okay, if there's enough pressure and if the plug is well lubricated, okay, well, water's pretty well lubricated. So that water's going to get pushed out. It's going to go from the area where the pressure is atmospheric plus rho gy to where it's atmospheric. It's got length delta L, radius R. I already said that. So just a few questions you want to answer. What's the mass of the water plug? What's the net force on the water plug? Through what distance does the force act? What's the change in kinetic energy of the water plug? And what's the exit speed of the plug? You can follow that chain of questions to derive something significant. The other thing that I guess I maybe better tell you is force always acts perpendicular to whatever surface it's acting on. Pressure force, okay? Pressure acts on the walls of the container horizontally, okay? It acts on the base of the container vertically. It acts on this plug perpendicular to the plug. So you got a force here. You got pressure acting on the plug in this direction. Okay. It's kind of necessary to have that. It's kind of something you would probably assume implicitly, but I'd better say it explicitly so you can deal with it. Okay, people stumbling a few things, you know, how do you get the mass of the water plug? Well, I've given you dimensions of the tube so you can find its volume and then multiply by the density. What's the volume? Cross-sectional area is pi r squared, radius is r, got a circular cross-section, and length is L. So there's your volume, and then you multiply that by rho.
If I laid a big old sheet of tracing paper on here, trace that curve and then draw it up.
A little hard to make a row right there with this chalk. Now, so far I'm just doing this with symbols. And that's the way you really want to do it, because if you do, it's going to apply to any fluid. Okay. So right there is the mass of the water plug in the tube. The net force on the water plug is what?
All of these nine are selected.
Well, net force is all the water plug over here. There's your water plug. I should have drawn it from the inside, but the net force is, well, on this side, the force is the area times the pressure in the tube, and I'm using P for the pressure of the water. I should probably have a subscript on that or something, but we'll just understand that P means pressure of the water, okay? And on second thought, I don't even want to do that. I want to do, what I used before was rho GY. So why not use rho GY here? Should have done that in the first place. And of course, we're still in symbols, so it doesn't matter even what altitude we're at. We can figure out the atmospheric pressure and add it, right? Turns out it doesn't matter, but we could do that. And then that's on this side. And on this side, we have pi r squared times the atmospheric pressure. So the net force is just rho GY times pi r squared. Okay. Yeah, you got the water pressure plus the atmosphere. This part of the water here is holding up the atmosphere. At least section of atmosphere directly above it, all the way up to where the atmosphere pretty much peters out to nothing. Okay. I mean, there's a lot of stuff out there, but it doesn't exert much pressure. Okay. So you add that pressure to this pressure and you get the pressure at this point. That's your atmospheric pressure plus your rho GY pressure. On the outside, you just have the atmospheric pressure, which is pushing this way, and this pressure is greater than this pressure, and there's the difference. So the net force on the water plug, well, there it is. So through what distance does a force act? The force acts when the water plug goes from here to here. Okay. Ignore the fact that there's another water plug coming in right behind it, right?
So that's the lecture.
All we're interested in is what happens to this water plug. Next water plug can take care of itself. Gonna have a little less pressure. All right, so we're gonna say that the distance it acts through is what? It's delta L, isn't it? Okay, so we can even draw a picture. We have the plug. Goes from here. A little hard to draw that. It essentially goes from here to here, a distance of delta L. Let's say from here to here. I'm not sure that's a good picture. I'm pretty sure it isn't. But it's got to move delta L to get out. Okay, so that distance is delta L. If you can make sense of that picture, okay, otherwise ignore it. Okay, what's the delta K of the water plug? It's a net force times distance. That ought to be automatic, but of course, part of what we're doing now is refreshing you on a few things that you might not remember. Net force is rho g by pi r squared. Distance is delta L. And notice, of course, pi r squared delta L is just the volume. Okay. And that's important. So the exit speed kinetic energy and mass rho times pi r squared delta L. Well,
Because I feel like it's a loss.
1/2 mv squared equals K. If you plug this in for M and plug this in for K, the pi r squared delta L and the rho are going to disappear. You're going to get V squared equals 2 GY. That's the same speed you would have if you just drop the water from here to here.
And if our function was this,
Because if you drop the water from here to here, that potential energy is going to, the potential energy change is going to equal the kinetic energy, right? If you run it through this tube, in the ideal case, if there's no friction, the change of potential energy is going to equal the kinetic energy. It doesn't matter if you drop it or run it through that tube. Now, in the real world, it does matter if it's water and a tube because there's friction. See how much time we got? We got a little time left.
so our question.
Okay, what happens in the tube? I'll exaggerate the length of the tube, although that's about what it's shaped like in this thing. Okay. The water at the center maybe moves at this speed. Okay. The water at the walls of the container adheres to the walls of the container and pretty much moves at 0 speed. Well, you don't have to get far from the walls before the water has some speed, but it's slower near the walls than it is near the center. And that's where your friction comes in. So you got, like, if you look at the tube from the end, it's like you can have a bunch of concentric cylinders in here. Okay. Or concentric cylindrical rings. In each ring, as you move toward the center, is moving a little faster than the one before because each ring is retarding the other due to the viscosity. Okay. And that's a pretty good picture of what's going on here. That's why there's energy loss. The viscosity actually heats up the water a little bit. I mean, the viscous forces. The energy stays there, but it goes into heat. So, you know, you don't want to let that water get on you. It might burn you. Coming out fast enough with enough pressure and not vaporizing as it comes out, you know, you could get some heat. But That'd be interesting to work out. I've never worked that out. It wouldn't be difficult. But there are limits to what we can do. Hang on. Okay. Gotta find my white chalk. Can't write Bernoulli's equation in Poland. All right.
Worried about dividing by two, but because there was two values, I'm gonna put it on zero, case. What about where root? Where root don't think square root is negative value, it's that is got.
That's a form that I prefer for Bernoulli's equation. It says that this thing in parentheses is constant. Okay. This is for ideal fluid. Ideal case for continuous fluid. In other words, what happens in this cylinder is not continuous with what happens in that cylinder, unless somehow I've got a tube running from this cylinder into that cylinder. Otherwise, you don't have continuous fluid. You don't have a continuous path from here to there. If I connect two cylinders together with a tube, now I have a continuous path. Of course, I got a tube where there's all kinds of pressure loss. It's still not an ideal case, but this is where you start. Now, what do you see here? Okay, I'm just going to ask. So that, okay, so rho is like mass over volume. So this is like 1/2 mv squared over v. Well, that's kinetic energy over v. Rho is mass over volume. So this is like mgy over v, which is potential energy over v, gravitational potential energy. And we might as well put grav on there. Okay. And this is like work done. And that's a little harder to explain, and we're out of time. And I wasn't going to try to explain that today because I've put enough on you. Okay. Now for homework, check the assignments page. I'm a little behind on things because I was not able to communicate with my students yesterday because nothing was working. And there are some students in other courses that really need me to communicate with them today. So I think I'll get this up by tonight. But I'm sure you've got other things to do. And we're probably going to have several days to do this stuff in. Okay, so I'll clarify, and then we can clarify that in lab on Friday, which will be 11 o'clock.
Yep.
You good?